Hey everyone, welcome back. I hope you watched my last two videos on the topic of natural language processing, and we kind of focused a bit on GPT because why not? That's exactly what's happening nowadays. And this one is in response to some of your questions about understanding a little bit more about the Subword tokenization. So the goal for this video is to make sure you understand what the tokenization means, especially what Subword tokenization means, because we understand what word is. Each word is a separate token. So if you have 5,000 unique words, then you have 5,000 tokens. And we also have letter, or individual alphabet level tokenization. And I don't think many people use that anymore, especially for this type of natural language processing. So with this goal, let's go ahead and jump in. And again, as usual, if you would like to get informed of these videos as soon as they are released, it's a very good idea for you to hit the subscribe button. And if you're feeling generous, try to find the thanks button that's right next to it. Okay, now let's jump in to see what exactly we mean by Subword tokenization. First of all, the philosophy of this algorithm is that frequently used words should not be split into smaller subwords. I hope that makes sense. If there is a word, I don't know, called algorithm, and in the corpus in your document, if that word comes up quite a few times, then it does make sense to use the entire word algorithm as one token rather than breaking it down into ALGO or ALGO. GO can be a token, right? It's go. That's a word itself. So the philosophy is if it's frequently occurring, then don't break it down into smaller words. And rare words should be divided into meaningful subwords. So if algorithm is a rare word in your training data, then it may as well be broken down into AL, GO, and maybe I don't know, R and I and so on. You get the point. So that's the philosophy here. And I gave an example right here. So if you want to use or look at the term DigitalSreeni, it's obviously not a real word that is in the vocabulary, right? Unless I get super famous and then everywhere it's like, hey, DigitalSreeni, there's DigitalSreeni that, and you have a lot of high frequency when it comes to DigitalSreeni. But until that happens, this word is basically, it doesn't mean anything to language models. So the way when you are tokenizing it, the way it can divide this is first digital, because digital is a very high frequency word. So that may be the token itself. And then SR, probably E, and NI. Maybe NI again, because NI comes as a beginning or in the middle of a lot of sentences or a lot of words, I should say. Then it makes sense for NI to be together. I don't know if SR makes sense to be together. We'll go through this and hopefully it makes more sense once we look at a couple of explanations, let's say. And why? What's the advantage of Subword tokenization? Because this way you do not end up with a very large vocabulary size. Because if you have 100,000 unique words, you don't want 100,000 tokens, right? I mean, or a million unique words if there are a million unique words in English. But you get the point. So you want a finite vocabulary size that you can actually handle. At the same time, you're not sacrificing the ability to provide the context dependent representation, because the entire natural language processing depends on the context based representation, right? So that's one. And of course, you can handle rare and out of vocabulary words by breaking them down into subword units. Just like I mentioned, DigitalSreeni can be broken down into digital and other subunits or subwords, if you want to call that. Okay, so now there is something called BERT tokenizer and BPE. So I'll get to the other one in a second, but BERT tokenizer, as the name suggests, it's used in the BERT type of architectures, which is bidirectional. So how does it actually work? So let's look at the sentence. Like, DigitalSreeni is a great resource for Python, which it is. You should believe that. And you will believe that once you watch all my videos. Okay, so if that's the sentence, then I pass that sentence through BERT tokenizer. And what you will see is this is literally an output that I got from, we'll do this exercise in Python if you are patient enough to go through this tutorial, which I don't think is going to be that long. But yeah, the encoded sentence is literally digital SREENI, and then is a great resource for Python. If you see here, first of all, the double hashes in BERT tokenizer, every tokenizer puts their own unique characters to convey something. In this case, 2 double hashes mean you should combine that with the previous one without leaving any spaces. That's why DigitalSreeni is like, all double hashes. And yeah, that's pretty much it there. And DigitalSreeni is not present in the tokenizer vocabulary, like I already mentioned. That's exactly why it's actually split into digital, SREEN, and I. All other words are in the vocabulary. E is in the vocabulary, a great resource for, and Python. All are part of this vocabulary except for obviously DigitalSreeni. That's exactly why it's broken it down. The other famous encoder, I should say, is Byte Pair Encoding, and GPT uses this, for example, and many language models use this. And this is based on the paper that you see on the screen from 2016, Neural Machine Translation of Rare Words and Subword Units. So that's exactly what Byte Pair Encoding. I will leave the link as part of the description in case you want to read this further. But let me quickly summarize exactly what Byte Pair Encoding actually does. So it starts with a pre-tokenizer that splits the training data. So you have your training data, it splits it into words. That's it. Basically, it's looking for spaces, and anything that's not a space, like these are different words. So that's how pre-tokenization actually works. And that's one way of pre-tokenization. And it can be, like I just mentioned, a space tokenization, or it can be a bit more complicated, rule-based, for example. And GPT uses just a simple one, just a space tokenization, where it's like, okay, you have a space, so this must be a word, this must be a different word. And using these pre-tokenized tokens, it learns how the merge rules need to happen to form a new word. So it's an iterative process. Because it takes 2 tokens and tries to see if the merge actually makes sense. And it's iterated until the vocabulary has whatever attained the defined vocabulary size. For example, that's a hyperparameter. You can define that, okay, I want my vocabulary size to be 5,000. So until the 5,000 is reached, it does the iterations over there. So let's see if we can make a bit more sense out of it. So here is a pre-tokenization and word frequency. For example, I looked at a document that I have written, like a couple of paragraphs, and then the word source appeared 10 times, you appeared 15 times, and tube appeared 5 times. YouTube actually appeared a few times, and YouTube appeared 5 times, and you appeared another extra 10 times. So I separated you and tube into 15 and 5. This is where we are. Okay, now what happens as the next step? So the base vocabulary, it's looking at, okay, so what's the base vocabulary? When you break everything down, you have S, O, U, R, C, E. So it's actually all the way down to byte level, right? So this is what we're talking about. So we are now down to byte level. So we have an S, we have O, we have U, and O and U occur multiple times, but it doesn't matter. We are just breaking it down to byte level. Now, the word split to base vocabulary. Now, if you take the source and U and tube, that's what you see. S, O, U, R, C, E occurred 10 times. Y, O, U occurred 15 times. Tube occurred 5 times. Now, this byte pair encoder actually counts the possible pairs and picks the pair that shows up more frequently. So what's the pair that actually shows up more frequently? If you look at O and U, shows up here, O and U shows up here, but you don't have O and U there. So, but O and U is the one that actually shows up how many times? 10 times here, 15 times here, so total 25 times. This is only 3 words in the vocabulary. Just imagine having 10,000 words. You will find higher, not just one example, you'll find many examples, but I'm just showing you one example of O followed by U. It occurred 25 times. So the first iteration, it learns to group O and U. It could be more, right? So in this example, it learned to group O and U. So the vocabulary, our vocabulary, after the first iteration is whatever I had initially plus O and U. I hope that makes sense. And then the words split to vocabulary after the first iteration. So let's go back to this SOURCE and 10, right? So we have that 10 times. If you actually split to after the first iteration, you have OU right there instead of O and U. And you have OU right here instead of O and U. And now the iteration continues. That's it. So this is how byte pair encoding actually works, and I hope this is a simple enough explanation. I don't know how else to kind of break it down, but this is pretty straightforward, I hope. So it's basically number of iterations. Luckily, we have multiple libraries where we can import our byte pair encoder, so we don't have to code this, but it's always good if you understand exactly what that means. Okay, now there are two variations, at least, that I would like to talk about. One is byte level BPE tokenizer and sentence piece BPE tokenizer. These are the two that are common, I should say, to use. And I almost said these are the two that I use quite often because I don't do natural language processing quite often. I do image analysis, but I do I do natural language processing as a hobby. I love it, but these are the ones that I kind of end up using quite often. Okay, so what does that mean? First of all, let's look at byte level BPE tokenizer. As you can imagine, it's byte level. So the tokenizer from the Hugging Face tokenizers library, so this is available from the tokenizer library, which is by the Hugging Face guys. And it starts by splitting each input text into bytes. So the previous example I showed you in the previous screen was exactly the byte level BPE tokenizer, where we're dividing that into bytes and then learns the vocabulary using the algorithm that we just talked about. Okay, and this is useful for languages with non-Latin scripts. If you're not just doing English, if you're doing some training in, let's say, Hindi or Chinese, or does it work with Arabic? I don't know. I don't know how to read and write Arabic, but most of these language models are going from left to right. So with Arabic, that can be a bit tricky when you write from right to left. I have no answer to that. But if it comes to non-Latin scripts, where character level tokenizer probably doesn't work well because the way you mix these alphabets to create a new alphabet is different. But in these cases, byte level actually works very well. Now, the sentence level, as you can imagine, it is a tokenizer. First of all, it's from the sentence piece library. And it first tokenizes the input text into sentences. So instead of breaking down based on spaces where you're separating words, this is breaking down obviously using periods, right? So you have a long sentence, and then trains a unigram language model on the result. And I do not know exactly all the details of this, but I know that this is exactly what it does. But again, this is available as is. You can, I'll show you how to use it basically. And it can handle a wide range of languages and text types, and again, learn both at the, it can also learn at the character level and the word level. Now, which one is better, which one to use in what situation? I have seen more than 70-80% of the time people using byte level BPE tokenizer. So I would focus, I would start with that. But it's a good exercise to actually test both of these and see how things are being tokenized using either of these. Okay, so now that we have some understanding, let's jump into Python code and just implement or not implement, use some of these from standard libraries. Okay, so let's go ahead and look at a couple of libraries. First thing first, go ahead and install the transformers library and tokenizers library. So this is where we have certain tokenizers. So let's start with the transformers library, where you have BERT tokenizer. We talked about this, and this is exactly the example I showed you earlier. So from transformers, again, by the way, I'm just using Spider IDE. This can work in your Google Colab. It doesn't matter. And in the backend for some of these, it's PyTorch. So make sure you have PyTorch installed, latest version with GPU enabled and all that stuff. So in case you wonder, let's go ahead and see what I'm using. Import torch. And I'm using 200 CPU. I have another environment where I have GPU, but I cannot run latest torch on my GPU. So I'm kind of stuck with a slightly older torch version. But for this demonstration, I thought it didn't make much of a difference. So yeah, I'm gonna use CPU for now. Okay, so transformers BERT tokenizer, let's go ahead and import that. And now we can import, again, in this case, we are importing from pre-trained the tokenizer. And let's go ahead and define our input sentence, which is DigitalSreeni is a great resource for Python. And now go ahead and tokenize it using the preloaded or pre-trained BERT tokenizer. You can train your own tokenizers using your vocabulary. I'll show you. I mean, I was working on something else, but I'll show you exactly how you can continue work, not just investigating tokenizers, not just understanding tokenizers, but taking that and how can you kind of put that in a natural language processing, for example, GPT-2 training from scratch. Yeah. Okay, so this is the input sentence. Normally, you don't just work with sentence, you work with a large corpus, but let's, for demonstration purposes, that's fine. And BERT tokens is basically tokenizer.tokenize, and go ahead and apply that on this text that we have here, and go ahead and print the tokens. And this shows you exactly what I showed you in the presentation earlier. And we know exactly what these two hash signs means now, right? And I also add, again, I'm going to share this file with you so you have all the text that I have up here. Now, let us go ahead and import the tokenizers library. In fact, from the tokenizers library, we are going to import sentence piece BPE tokenizer. And the process is very similar. You import the tokenizer, you initiate the tokenizer, and then you have an input sentence. And in this example, I'm not using a pre-trained. In this example, I'm using a pre-trained, right? So go ahead and get the pre-trained and then apply that onto the sentence I just created here, onto the text. But in this case, I am going to train it on my own text. And I think my own text is some text. And let's go ahead and check that out. Some underscore text. I just wrote something. In today's world, coding has become blah, blah, blah. Python is a powerful resource. So I just, in fact, I generated this via ChatGPT. I asked it, hey, can you write 5 paragraphs about Python and the importance of coding? And it gave me 5 paragraphs that I'm using for training here. Okay. So what are we doing? We imported sentence piece BPE tokenizer, and let's go ahead and import that if we haven't done that. Yeah, and let's go ahead and instantiate that. So that's what we're doing. And now my input sentence is DigitalSreeni is a great resource for Python, and all my friends love DigitalSreeni videos on YouTube. As you know, YouTube has many channels, but I like DigitalSreeni. So I try to repeat DigitalSreeni multiple times, as you can see, because I was testing if it sees the frequency now. Okay, you have many. So is it going to break it down like this DigitalSreeni into digital and something else, or is it going to leave digital as is, right? So let's go ahead and check that. Let's read our input sentence. Now let's train on our own vocabulary. So in this case, we have some text right there. BPE sentence tokenizer that we instantiated. We are going to train that with a vocabulary size of 1000. So let's go ahead and do that. And now let's tokenize it. So our input sentence, let's go ahead and tokenize it. And let's go ahead and print it so we can see how the tokens look like. And as you can imagine, it actually left DigitalSreeni as is. And is 1 and A and G. So there are certain, so these are all different tokens in the sentence. And DigitalSreeni again is a token by itself, and as you can see, OU apparently repeated multiple times. So OU is like one token right there. DE, same story. YOU, same story. So now you get an idea of how this sentence piece BPE tokenizer kind of is working. Let's do exactly the same to byte level BPE tokenizer. You may not see much difference. Let's actually see what we get. And the process is identical. Instead of this, I'm just calling a different tokenizer. That's it. So byte level, let's go ahead and instantiate that. Let's put our input sentence and let's train it on the same text from before. And let's go ahead and generate the tokens and go ahead and print the tokens right there. And you can see it's giving pretty much very similar response, except here, I think THON. I don't think, oh yeah, THON. They're very similar responses, as you can see, IS. And in this case, it's putting a underscore as a prefix to tell us that it's used to represent the beginning of a word. So in this case, it's using this G dot as the beginning of a word. Yeah, so when you see GIS right there, that basically means DigitalSreeni space IS is a separate word by itself, A, and so on. Okay, so there you go. So those are that's how you tokenize it, and that's the difference between these different tokenizers. And I added more text here, but one thing that I want to show before quitting, in fact I'll also show something else if you want to hang out, but there is a way of actually training versus training from iterator. You see these two, and initially I was scratching my head in terms of what's the difference, because here we are training, right? So when you do tokenizer.train and you're training it on like a file, so there is another thing called train from iterator. The primary difference is, as you can imagine, it can be applied on an iterator, right? Train is not applied on an iterator. Train from iterator is an iterator. So when would you use that? First of all, the train method just takes a list of strings as input. And each string is basically a document. Hey, here is my document number 1, 2, 3, 4, 5, 6, and then it takes those, it reads everything into memory, and then it creates this text, and then and then it kind of performs this training of tokenization on all the text that it actually loaded. Now, if you have a tremendous amount of text that doesn't fit into your memory, then train from iterator is probably the best way. You create an iterator out of all the files that you have, and then it loads one at a time. So a quick example is what I showed you here. So here it's actually, I have 3 files, some text2.txt, some text3.txt. So I have all of these. It actually combines all of those, and there you go, and single training right there. Or if you create an iterator, you can create an iterator like this from document iterator. You have like text1, text2, text3, and then go ahead and yield. And if you do train from iterator, now it's actually doing one thing at a time. That's basically the difference right there. Okay, so originally that's what I wanted to cover in this video, but I'll just give you extra bonus instead of making this another tutorial. Maybe I'll do a in-depth one in future, but for now I want to make sure, okay, now that we understand these tokenizers, let's let's say train GPT-2. I cannot train GPT-3 or 4 model because I don't have the models. They haven't made them public. But GPT-2, yes, we have them available, so we can try to train them. So how can you train those from scratch? In fact, let's clean everything so things look a bit clean from our side. And let me go ahead and zoom in. I forget to do this in some videos, and I have to re-record it. Okay. Now, the purpose of this code is to train a GPT-2 language model from scratch with custom vocabulary. Let's say we have our file. I think I just downloaded. It's always dangerous to show something I haven't tested yet, but let's find out. I literally just downloaded this Hitchhiker's Guide.txt. It's basically the book in the text format right there. Okay, and I want to train it on this text file and generate some text. Don't expect miracles here, because this is language models. They require a tremendous amount of data, tremendous amount of training time. Otherwise, you get kind of crap. And let's see what kind of crap we can generate today. So first of all, we are going to import the tokenizers library. Let's import the tokenizers, and let's also import transformers. The transformers library is great because now we're not trying to put together individual architecture. You can, if you want, like bring in a transformer and then dropout layer, do something else, and you can put your own architecture. But I am going to import the GPT-2 LM head model, and then the tokenizers and so on, so I don't have to put together the model myself. I don't have the skills to put together an amazing language model myself, so I'm going to use this humongous model. Although with little amount of text, probably a small model works much better than such a humongous model like GPT-2. Okay, so I'm talking a lot, I'm not showing you, so let's go ahead and jump in. Now, in this case, I'm going to define my input directory. I can throw 100, 1000, how many ever files in this directory. And I am saving the tokenizer to a tokenizer model directory, and model, the actual model, to a model directory. And let's first create a customized vocabulary, right? So first we need to create our own vocabulary from the text files that we just are going to read right there. And then we'll get to GP2 language model, where we'll take our custom vocabulary and add to what GP2 already has, right? So yeah, let's go ahead and start there. And I am going to use byte level BPE tokenizer. Now you know what it is. So now you see how I'm using it in the context of training a natural language model. Okay, let's go ahead and get our text, our vocabulary ready. We only have one text here, but it doesn't matter. It works if you have a bunch of text files. This may take a few seconds because this is a very long text file. Okay, there you go. And now save the tokenizer. So all we are doing here is we are actually opening each files, reading them, and we are capturing them as a text variable. And that text variable I am going to tokenize, train from iterator, and vocabulary size is 5,000. So basically that's typically, if you have a lot of text, then 50,000, 100,000 vocabulary size is probably common. But in our case, let's just leave it to 5,000 and see what we get. So from here, now everything is tokenized. We want to save that into our output directory, which is basically our tokenizer model directory, because I'm going to import it later. Okay, so now we are ready for our GPT-2 model. So we can get that from the transformers library, and it only works with tokenizers that are of the transformers format. So the save tokenizer that we just did, the BPE tokenizer, it has to be loaded into the transformers format. In other words, we'll just use GPT-2 tokenizer. You can use fast or regular, it doesn't matter. Use that to load the other tokenizer that we actually just saved. So that's what we are trying to do here. So GPT-2 tokenizer from pre-trained. If you remember from my last tutorial, literally the one before this, we loaded this pre-trained from a pre-trained GPT-2 model. We also loaded a pre-trained model right there for GPT-2 using the pre-trained. So some aspects look very similar, except we are just training everything from scratch in this case, using our own directories. Using our own data in this specific directory. Okay, let's go ahead and load this, and the output directory is the one where we stored our tokens. And let's go ahead and padding. Go ahead and read upon these. I don't want to make this any more longer than it needs to be. And okay, so now let's go ahead and initialize the GPT-2, I'm struggling to say this, language model with the same vocabulary. So let's go ahead and load that model, GPT-2. It probably takes, if it's the first time, it'll download that model first, but you can see, I'll share the code, so don't worry about it. And another way of actually learning, if you think I'm going fast or I'm not explaining every line, you can just take this code or a specific line, put it in ChatGPT, and it's like, hey, by the way, what is this? It provides much better explanation than I can ever provide. Obviously, it knows a lot more than I do anyway. So input file is where we have our tokenized new tokens, right? So the ones, the tokenized I'm struggling today, obviously, or tokens where we saved this, which is output our tokenizer model, and from here is where we are loading that. Okay, so that is where we are input file, output directory. Okay, so that's what's being loaded, and now tokenize the input text using GPT-2 tokenizer. So let's go ahead and tokenize that using GPT-2. Again, it sounds like multiple tokenizers. We have this original tokenizer that we trained on our own vocabulary. We are loading it, and now we are converting that into something that our GPT-2 can understand. That's pretty much it. And now load the tokenized input data line by line. Let's go ahead and create this data set. And now you can create, okay, what is the block size and what tokenizer you're using, and define the training arguments. Again, this is self-explanatory in most cases, like number of training epochs, for example. Yeah, so 5 epochs, and save steps, how often do you want to save, and all that stuff. We are just doing only 5 epochs, so it should be pretty fast enough. And now let's define the data collator. And again, that basically means it helps in grouping and batching individual sequences together. Go ahead and read more about what data collator can do. but that is a parameter that you can actually supply to the trainer when you're training the language model, which is exactly what we are doing next. We are defining the trainer object, and then we'll go ahead and train the model right there. Yeah, let's go ahead and train it. I haven't trained this model on my CPU. It probably takes a little longer, but still we don't have a lot of text. It should be relatively fast. Yeah, there you go. So yeah, so let's see, go ahead and save it, and let's see what type of text we generate. I'd be shocked if it's any meaningful, but that's okay. Let's go ahead and check. So import transformers, from transformers. Okay, this is, we saved in model, we saved in tokenizer model. Yeah, let's actually run everything. And by the way, for input, you need to give some seed text, and I just gave the seed text as meaning of life, and let's see what it does. So let's go ahead and print. There you go. Okay, meaning of life, off, whatever it's saying. Let's do something else. Let's say the life's ultimate question. Let's say life's, I don't know what the answer is, but let's just go ahead and type. Yeah, question is, again, it's struggling, obviously. With 5 epochs, that's exactly what you would expect, but go ahead, I'll share the code, go ahead and play with, it's not just about number of epochs. On this text, if I do, I don't know, 10,000 epochs, I may get slightly better result, I may not get slightly better result, but the entire thing, it comes down to training it on thousands and thousands of these text documents for you to get anything close to ChatGPT, anything close to ChatGPT, right? So with just one text document, not much you can do, but it's fun exercise. So anyway, the intention was to teach about tokenizers, especially talk about Subword tokenizers, but I hope you appreciate the extra stuff that we went through, which provides the context in terms of what it means. What does Subword tokenization mean, and how does it relate to language models? So now I hope you get a good idea in terms of what is going behind ChatGPT 3 or GPT-4 or other language models. It doesn't matter. Anyway, guys, this is already too long now, and thank you very much for being very patient. And again, do not forget to hit the subscribe button. Let's meet again in the next tutorial.